Hello everyone. So welcome to Turbo Machines, and so we are going to solve some numericals in this video. So earlier we have seen in the previous videos what we have seen is like impulse and reaction turbines definition, and then types, classifications, and working principle, and different types of compounding like pressure compounding, velocity compounding, pressure velocity compounding both combined, and then how to draw the velocity triangles and how to draw combined velocity triangles, and at the same time along with that work done efficiency and blade efficiency, and then maximum blade efficiency. So all these things we have seen in this module, and now we have come to an end. So by solving these problems, so we'll understand even more better. Okay, so we'll move on to the problem. So the numerical is like this, and the first one is dry saturated steam at 6.5 bar with negligible velocity expands isentropically in a convergent divergent nozzle to 1.4 bar and dryness fraction 0.956. Determine the final velocity of steam from the nozzle if 13% heat is lost in friction. Find the percentage reduction in the final velocity. So this is the problem given here. So dry saturated steam. Okay, so first and foremost, before solving this problem, so we should know what are the different types of steam available. So there are three different types. One is wet steam, second one is dry saturated steam, and the third one is superheated steam. So wet steam, so there will be a combination of wet particles and dry steam. There is a mixture of both. And dry saturated steam is dryness fraction is 1, that is 100% dry. There is no wet particles present in the steam. And apart from that, there will be superheated steam. So if you supply heat for dry saturated steam, so it will become superheated steam. So it will possess some energy. So in this problem, so it is given as dry saturated steam, that is 6.5 bar, that is P1 is equal to 6.5 bar with negligible velocity expands isentropically. Isentropically means it is an adiabatic process. So in a convergent divergent nozzle to 1.4 bar. So P2 is equal to 1.4 bar. So that is the pressure is reduced, the pressure drop takes place from 6.5 bar to 1.4 bar, and dryness fraction is 0.956. So here the dryness fraction is given in this problem. That means so the steam is not dry here. So it has changed into wet steam. So wet steam means there will be some amount of dryness fraction will be there. So that is 0.956. That means 95.6 percentage of dry steam is available. So remaining 100 minus 95.6 percentage will be the wet particles which are present in the dry steam. So that means, so in this problem, so the first initial pressure was 6.5 bar. So once the adiabatic process, that is a adiabatic expansion process, so pressure drop takes place. That is 6.5 bar to 1.4 bar, it has changed. Therefore, so the steam has converted from dry saturated steam to wet steam. So this is the scenario which is given in the problem. So determine the final velocity of steam, that is, so V2 they are asking us to find out from the nozzle if 13 percentage is heat is lost in friction. So because of the friction in the nozzle, so 13 percentage heat is lost. So find the percentage reduction in the final velocity. So how much, so what is the final velocity? First we have to find out, and then so what is the percentage reduction because of 13 percentage heat is lost in friction. So what is the percentage reduction in the final velocity? So that is what we have to find out in this problem. So first let us take down the vertical data which is given in the problem. So first one is exit pressure is given. So initial pressure is P1 is given as 6.5 bar. So we have to make note of this P1 as also as a 6.5 bar. And then exit pressure, that is P2, that is equal to 1.4 bar. And then dryness fraction is given, which is x2. So why here x2 is taken is because why can't we put x1 is, so already x1 is 1, that is 100 percentage. So then dryness fraction for the initial pressure is 1. So x1 is equal to 1. So it is not given, but it is understood. So here x2 is given. So x2 is equal to 0.956. And also it is mentioned in the problem there is a heat loss, that is 13 percentage. So here we need to find out the percentage reduction in final velocity. So from steam table for initial pressure P1 is equal to 6.5 bar, take values. So here, so we need to take the values from steam table. So from the steam table book, so we have to take P1 pressure. So we have to take the dry saturated steam table. So in the dry saturated steam table, so we need to locate where pressure P1 is 6.5 bar. So in the steam table 6.5 bar, the corresponding values, that is initial enthalpy, that is H1 is equal to 2758.8 kilojoules per kg. At the same time, so here H1 only it is taken. Why? Because so this is the dry steam. So that means a total steam. So total amount of heat energy is available in the initial condition. At the same time, similarly at 1.4 bar. Now this 1.4 bar is nothing but wet steam. So there will be some amount of wet particles present in this. So from steam table, so we need to locate where that 1.4 bar is available. So we need to locate that 1.4 bar and then corresponding values, that is HFG2, that is 2231.9 kilojoules per kg, HF2, that is 458.4 kilojoules per kg. Then finally we need to find out the H2 value, that is H2 is equal to HF2 plus X2 into HFG2. So where H1 is equal to, so there is no dryness fraction, that is X is equal to 1. So it is a direct value, total value. But for H2, since it is there is some amount of wet particles are there in the steam, since dryness fraction is given as so 95.6 percentage, so we have to take this formula, that is H2 is equal to HF2 plus X2 HFG2. So all these values are known to us. So we will substitute these values and finally we will get the value for H2 as 2592.1 kilojoules per kg. So this is how we need to find out the final enthalpy. Okay, so now we know initial enthalpy and we know the final enthalpy. So next we need to find out the final velocity. So how to find out final velocity? Final velocity V2 is equal to, there is a formula, R into T into 2000 into H1 minus H2. So there if you substitute all these values, so we will get the value as 577.39 meters per second. And then so there is, it is given as a heat drop is taken. So that is so here in this R so how to find out this final velocity? How do we get this value as 577.39 meters per second is? So from steam table, so you need to find out, so what is the value of universal gas constant, that is R, and then temperature into 2000 into H1 already we have found out, that is 2758.8 kilojoules per kg, and H2 is equal to 2592.1 kilojoules per kg. In this we can see the difference, H1 value is more and H2 value is less, because of the presence of this wet particles, so H2 has come down, that enthalpy of final enthalpy has come down with compared to initial enthalpy H1. So if you substitute all these values, we will get V2 is equal to 577.39 meters per second. So next one is heat drop, that is 13 percentage. So we can take it as 0.13. So nozzle efficiency is 1 minus 0.13 is equal to 87 percentage is the nozzle efficiency, that is 0.87. Now velocity of steam by considering the nozzle efficiency, if you consider the nozzle efficiency, then the value will be V2 is equal to R into T 2000 H1 minus H2 into we need to multiply with nozzle efficiency. So that is equal to V2 is equal to 538.55 meters per second. So already we got so V2 value as 577.39 meters per second. This is without considering the nozzle efficiency. By taking 100 percentage of nozzle efficiency, we got this value. By taking this what we call as 89 percentage, like 87 percentage, if you consider, then it will be 538.55 meters per second. So now if you calculate the percentage reduction in final velocity, so initial minus final, that is 577.39 meters per second minus 538.55 meters per second, then reduction in final velocity will be 6.72 percentage. So this is how we need to find out the problem. So we will solve one more problem in the next video. So thank you for watching this video.